Welcome to the introductory course on algorithms. So today is the introduction to this formal course on just algorithms. So in this course on algorithms, we are going to talk more, or rather we are going to focus more on algorithms, techniques to solve particular problems, techniques to come up with the design of new algorithms and concepts. Then we are going to talk about the design techniques, analysis part of those algorithms, rather than talking much more on the data structures that we use to solve particular problems, because that has been covered in the course on programming in C and data structures. So this is the kind of next level course on algorithms, where we solve the problem using that particular data structure. So to start with the algorithms, let us think about where can we actually start talking about the algorithm, the concept of algorithm itself. Can we come up with the formal definition of the algorithm? Is it really possible that much is it really that much easy to come up with that definition of algorithm? So let's start with the first attempt, which is the kind of semi-formal definition of algorithms. So that definition is, what is an algorithm? It is a set of rules defining well-specified computations to solve a well-defined computational problem. So this is our first attempt at trying to come up with the notion of algorithm and start formalizing it. So even in this definition, kind of semi-formal definition, we see few elements which really need much more attention. The element is, first of all, what is a computation? What do you mean by a computation? And the second thing is a well-defined computational problem. Well-defined computational problem. So first of all, what is a computation? Then what is a computational problem? Once we understand what is a computation, we will understand what is a computational problem. But again, that there is a concept of well-defined. So what is meant by really well-defined computational problem? We will see step by step. So let's start talking about computation. What is a computation? So computation is a sequence of simple local steps that we try to understand or solve. So let's discuss on this definition of a computation. A computation is a sequence of simple local states that we try to understand or solve. So what is really mean by simple state? What is mean by a local state? So the thing is that steps meaning simple is that every system where we solve a problem comes from some particular system. That particular system has got some very intuitive kind of operations attached with that system. So those intuitive kind of operations that we call as simple operations. Those are simple steps. And what is meant by a local step? Local step meaning we are really not talking about some particular action in that particular system, where we can actually achieve that particular action by using a composition of so many simple steps, the very basic primitive steps. If that is happening, then we will not call it as a local step. Okay, that computation we will not call as a local. For example, what is not local? What is not local in arithmetic is compute a raised to n for some Why is it not a local step? Because we really do not have any operation in arithmetic which allows us to do power computation as a basic primitive step. What we have is plus, minus, into and division. So we can really perform this exponentiation operation using multiplication. We have a raised to n is as the product of a with itself n times. So it is not really a simple step, it's not really a basic primitive step, it is a composition of n multiplications, n minus 1 multiplication rather. So that is not a local step. What we call as a local step is a into a. This will be a local step for this particular problem, this particular system, arithmetic system where we are trying to solve a problem, we are trying to talk about a computation of a raised to n, computing power of n power of a. So now we know what in the computation, what are simple computations, what are simple steps in computation, what are local steps in computation. So is it really true that whenever we talk about computation, that computations, the examples of computation come from only arithmetic or from science or from maybe physics, chemistry or engineering problems? It's not really true that way. Like in school, we have learned the multiplication problem and addition and finding roots, square roots, solving algebraic equations. These are definitely computational problems, but it is not necessary that the concept of computation is restricted only to these formal systems. So from this definition, we can see that we are actually going beyond the scope of science, let's say not science, but the formal systems that we have learned, because of the very basic elements involved in the definition. These are simple local steps. Steps meaning a step-by-step evolution of the system from initial stage to the later stage in the system. So in real life, where we can actually see the example of computation is that, let's say, hair loss. Hair loss is a particular system where a particular person has got some density of hair, and something happens and then the density reduces. So this is the initial stage of this particular hair density system, and this is the observed later state. What has happened in between is that the system has transformed from initial state to observed later state. Whatever, definitely there is a sequence of some operations, some genetic changes, or maybe biological things which I'm not specialized to talk about, but there is something definitely going on step by step, okay, or maybe in parallel, that is transforming this initial state hair, that is reducing this initial hair density into the later less dense hair system. So this is one particular example. We may not know exactly what is going on literally in each and every step. So that is why I have written down here that a sequence of simple local steps that we try to understand or solve. When we have enough knowledge, then we can really mention step by step whatever knowledge we have, use that knowledge to solve a particular problem. But here we can use lack of knowledge as our start to understand this particular computation system. This one. Second thing is weather evolution. We have some particular weather again. After some time, the wind change and everything, there is a change in the environmental system, and then we really see so many effects like hurricanes, blisters, and everything, and so on. So we have really a initial weather system. After that, something happens. There is a sequence of some steps which environmental scientists might be knowing, they definitely know, which are leading us to this observed later states. So what is happening in between is again a sequence of steps that is leading the system from this state to the final observed later state. So this is what is exactly captured in this generalized definition of computation. So it is not really necessary that when we talk about maths only and science and physics, the notion of computation is restricted to that. It's not really true. What we are saying is that the generalized view is evolution of the system from the initial stage to the final stage, what we call as a final stage. So when we have such a general definition of computation, what we know that from this, that computations are literally everywhere. What we know is that computations are literally everywhere. And because of a definition of semi-formal, kind of semi-formal introductory definition of algorithm involves computation. So in this subject, we are really talking about almost literally everything, because computations are almost everywhere. So that is why this subject is very much important to be learned, and the design techniques and the analysis part. There has been so much formalization and so much of interest in this subject because of this power that this subject is trying to use the kind of knowledge that we have attained over so many years of formal education of so many subjects to solve different problems, capturing the very notion of what is called solving. Okay, so to start with this is what we can say as a notion of algorithm when we talk about like just algorithms. Later on we will talk about what are computer algorithms, because we have to solve the system, we have to solve the problem. Definitely we are interested in solving, so we have to solve either by hand on pen or paper, using pen or paper, otherwise we'll be using some of the other system, some mechanical device or some electrical device or computer device, whatever the systems, we will definitely be using some kind of system to solve that particular problem. So we will be implementing this our notion of solution of a problem, step-by-step procedural solving of this problem, the implementation of algorithm targeting one particular system or device that we will be using to solve. So here we stop with the just introduction and notion of this concept of algorithm.